The problem with moving the moon isn't just that it's big, it's that we're trying to solve a massive engineering challenge with party supplies. Moving 7.346 times 10 to the 22nd kilograms of lunar mass would normally require rockets, gravitational assists, or science fiction technology. Instead, we're considering balloons? But that's exactly why this thought experiment is valuable. By systematically breaking down this impossible task, calculating the exact number of balloons needed based on their 14-gram lifting capacity, determining the required string strength, and considering atmospheric limitations, we learn a powerful approach to problem solving that applies to real engineering challenges. Let's start with Earth's gravity and work our way through each component of this lunar lifting system. Picture this. Earth suddenly stops pulling on the moon. That big gray rock would instantly become the most expensive space balloon as it drifted away. But gravity doesn't take vacations. It's always working. And that's our first big problem. Earth's gravity tugs downward with 9.8 newtons for every kilogram of mass. To put that in perspective, that's like placing 1,000 apples on a scale just to measure how hard Earth pulls on a single chunk of moon rock. Now scale that up. The entire moon has 7.346 times 10 to the 22nd kilograms of mass. Writing that out gives you 73 quintillion, 460 trillion metric tons. That's not just heavy. That's if you stacked elephants to form a bridge to the moon, you'd need more elephants than atoms in the observable universe. Heavy. Here's another way to think about it. If the moon were a watermelon at a picnic, Earth's gravity is that one kid who refuses to let go of it. The numbers seem ridiculous because they are. NASA's moon fact sheet confirms these figures. This isn't theoretical, it's the real crushing force we'd have to overcome. But here's the wrench in the plan. Gravity doesn't just affect mass, it scales with distance too. The moon is 384,400 kilometers away, and Earth's pull weakens with range. Still, even at that distance, Earth keeps the moon locked in orbit with about 1.98 times 10 to the 20th power newtons of force. That's not a typo. For comparison, the total thrust of the Saturn V rocket was about 35 million newtons. You'd need roughly 5.6 quadrillion Saturn V rockets firing continuously just to match what Earth's gravity does naturally. So why don't we feel this tug of war? Because the moon is also pulling back equally hard. It's a cosmic standoff, and we're trying to hijack that equilibrium with party balloons. Even if we ignored everything else, the strings, the logistics, the fact that balloons pop in space, gravity alone makes this a losing battle. Speaking of space, here's another complication. While the moon's surface gravity is only 1.62 meters per second squared, about 16% of Earth's, that doesn't help us. The challenge is Earth's pull, not the moon's own weight. A person weighing 68 kilograms on Earth would only weigh 11 kilograms on the moon. But that lightness doesn't change the absurd amount of force needed to counteract Earth's grip. Gravity wins this round, but let's say we ignore it for now. How many balloons would we need just to match the moon's mass? That's where things get even sillier. Here's the crazy part. A standard helium balloon can lift about 14 grams, roughly 2 nickels and a penny. Now picture this. To lift the moon's mass of 7.346 times 10 to the 22nd kilograms, we'd need enough balloons to offset 7.346 times 10 to the 25th grams. That's a 7 followed by 25 zeros. For context, if you lined up that many balloons end to end, the chain would stretch across the observable universe 500 quintillion times. But balloons alone aren't the issue, it's what connects them. Even if we magically produced enough helium, Earth's entire supply would cover roughly 0.00000000001% of what we'd need. The string tethering them to the moon would face impossible demands. Spider silk, one of nature's strongest materials, can handle about 1 gigapascal of stress. The moon's weight would require a material with 10 to the 23rd times that strength. Carbon nanotubes come close, but we'd need to manufacture more than exists in the entire solar system just to make a shoelace's worth of this cosmic rope. How stuff works confirms the 14-gram lift per balloon, and their calculations show how quickly this scales. To lift a 50-kilogram person, you'd need around 4,000 balloons. The moon weighs 1.47 times 10 to the 21st power, times more than that person, meaning we'd need approximately 5.88 times 10 to the 24th power balloons, a number so large it exceeds all the atoms in Earth's atmosphere. Even if we used massive 30-meter balloons, each capable of lifting 14,000 kilograms, we'd still require 5.25 times 10 to the power of 18 of them. That's enough to blanket Earth's surface 400,000 layers deep.